So hello everybody, welcome to lecture 2 of moving charges and magnetism. So let us begin with a few problems based on lecture 1. So we are dealing with the first one. In a chamber, a uniform magnetic field of 6.5 Gauss is maintained. An electron is shot into the field with a speed of 4.8 into 10 to the power 6 meter per second, normal to the field. Explain why the path of the electron is a circle. Determine the radius of this circular orbit. So if we begin with this particular problem, the problem is stating that the strength of magnetic field B is equal to 6.5 Gauss. So this 6.5 Gauss must be converted into Tesla. So 1 Gauss is 10 to the power minus 4 Tesla. So we write it as 6.5 into 10 to the power minus 4 Tesla. Now the speed of electron V is given to us as 4.8 into 10 to the power 6 meter per second. The electronic charge in this particular problem is asked to be taken as 1.5 into 10 to the power minus 19 coulomb, and the value of mass of electron Me is 9.1 into 10 to the power minus 31 kg. So the first question is asking us explain the why the path of the electron is a circle. So it is also explained in the previous lesson that if we consider that the region is having a magnetic field B like this, so on being projected in a region of magnetic field like this, so what exactly happens is we observe that the direction which the of the force is always directed towards the center, and this is the trajectory which the electron follows. So if this is the trajectory of the electron, we say that the direction of force is always along the center, that is always perpendicular to the value of velocity at that point. So the value of force is perpendicular to velocity at any point, and hence we say that this force is balanced by the centripetal force, that is mv square by r, and as a result of which it is moving in a circular path of radius r. So from here we calculate that the radius r in which it is moving can be determined as r is equal to mv by qb. So if we substitute the values, so we have 9.1 into 10 to the power minus 31 kg, V as 4.8 into 10 to the power 6. The value of charge in this problem is mentioned as 1.5 10 to the power minus 19, and that of magnetic field is 6.5 into 10 to the power minus 4. So all the values are in SI units, so the value will be obtained in meter. So we obtain a value equivalent to 4.2 into 10 to the power of minus 2 meter, which is roughly equal to 4.2 centimeter. So we consider that the electron is moving in a circle of radius 4.2 centimeter. Let us move to the next aspect. So in the next problem, it is stating obtain the frequency of revolution of the electron in its circular orbit. Does the answer depend upon the speed of the electron? So it is just a continuation of the previous problem, where the question is asking us to calculate the frequency of revolution. So the cyclotron frequency was calculated by us as equal to 1 by t, and t was equal to 2 pi m by qb. So we have it in this way over here. So if we substitute the value of each aspect, so we can write over here that the value of charge is 1.5 10 to the power minus 19, that of magnetic field is 6.5 into 10 to the power minus 4 Tesla upon 2 pi, and mass of electron is 9.1 10 to the power minus 31. So this is the value of frequency that we have, and on solving we obtain the value is equivalent to 18 megahertz. And the frequency of the electron is independent of the speed of the electron. Let us move to the next problem. So this problem is stating an electron emitted by a heated cathode and accelerated through a potential difference of 2 kilovolt enters a region with uniform magnetic field of 0.15 Tesla. Determine the trajectory of the electron if the field in A part is transverse to its initial velocity, in B part makes an angle of 30 degree with the initial velocity. So for this particular problem, we begin it out by stating the following aspects about it. So the value of magnetic field which is stated in the problem B is equal to 0.15 Tesla. The charge on electron E, which is equal to Q, is 1.6 into 10 to the power of minus 19 coulomb. The mass of electron is treated equal to 9.1 into 10 to the power minus 31 kg. It is stating that the electron is accelerated through a potential difference of 2 kilovolt. So we say that the value of accelerated potential is equal to 2 kilovolt, that is 2000 volt. So the kinetic energy of the electron. So the first thing that we calculate over here is the kinetic energy of electron. So the kinetic energy of electron is equal to EV, since the electron is accelerated through a potential difference of 2000 volt. So the value which it attains is equal to EV. So in this part we can write it as 1.6 10 to the power minus 19 into voltage, which is equal to 2000. So this is the energy which it is acquired, and we can equate it with half mv square to attain the value of velocity. So it is equal to 1.6 10 to the power minus 19 into 2 into 10 to the power 3. So from here we can say that the velocity of the electron when projected in the magnetic field is twice of 1.6 into 2 into 10 to the power minus 16 upon mass, which is 9.1 into 10 to the power minus 31 kg. So the square root of this value in meter per second is the value of velocity that we have. Now in the first part, the question is asking us to calculate the radius when its velocity is if the field is transverse to its initial velocity. So when the field is transverse to its initial velocity, so this time there is no angle part. So we say that the value of radius r can be simply calculated as r equal to mv by qb. So if we do the necessary substitution, so we can put the value of mass as 9.1 10 to the power minus 31 kg, charge as 1.6 10 to the power minus 19, and the value of magnetic field as 0.15 Tesla. So since the v is in a square root, so I'm squaring this entire parameter and introducing this also into the square root, that is 1.6 into 2 into 10 to the power minus 16 upon 9.1 into 10 to the power minus 31 is square root. So from here we calculate the value of radius equal to 1.01 into 10 to the power minus 3 meter. So it is roughly coming out to be 10 to the power minus 3 meter, and that is equal to 1 millimeter. Now in the next part, the problem is stating that it is making an angle of 30 degree with the initial velocity. So if we solve V part, the question is stating that it is making an angle of 30 degree with the initial velocity. So the velocity component perpendicular to the magnetic field will be the sine component. So we can write it as R equal to M V sine 30 upon QB. So we introduce this sine 30 parameter, and on solving for B part we obtain the value equal to 0.5 millimeter. So this is how we solve the second aspect of the problem which is being asked. So now we will be beginning with the further lessons. So previously we have introduced with the concept of Lorentz force. So we have read with one portion of the Lorentz force, that is we introduced with the value of F equal to QVB. So now we will be introducing to the another aspect. So as I said in the previous class, that the magnetic field and electric field are basically go hand in hand. So if they go hand in hand, it is necessary that we understand the effect of both of them in a combined fashion. So I say we are reading a small topic over here where I am stating particle in a region of electric field and magnetic field combined. So what is going to happen if the particle enters a region of electric and magnetic field in a combined way? So we are dealing with this aspect over here. So if I say that let us suppose that the electric field E is present in this region, which is represented as E vector, and magnetic field is present, which is represented as B vector. The mass of the particle is m and the charge is q. So the force which is experienced by this particle is going to be the force due to electrostatic, followed by the force due to the magnetic effect, and we say that the net value of force is going to be q E vector plus q V cross B. So the net value of force, or the equation of force, will become q E vector plus V cross B. So this is the net value of force which we have for a charged particle which is introduced in a region of electric and magnetic field combined. So we begin with the concept of velocity selector or velocity separator. So velocity selector. So now in order to understand this concept, we are taking a charged particle Q having mass m that will be projected in a region of electric field and a magnetic field combined, such that the electric field and magnetic field are present perpendicular to each other. So basically a velocity selector or a separator is a device through which we are able to identify a particular charge having a certain velocity. So how we do it, let us understand the concept. So we are first of all drawing two parallel large plates which is responsible for the production of electric field in the region in the I cap direction. So these large plates are responsible for the electric field creation in the I cap direction, that is somewhat like this. So this is going to be the direction of electric field, and it is throughout the plate. So if we consider that a charged particle having a charge q is projected in this region having charge q and mass m with a certain velocity v, so this force will try to take the particle towards the right, that is in the I cap direction. Now in order to nullify the effect, so if I want to nullify the effect of this particular force, so we introduce another two plates which will be creating magnetic field which will be directed into the plane of the region. So we are representing it in this way. So over here we are considering something like this, these green lines which are basically acting like the poles of the magnet and is responsible for creating a magnetic field B vector which is directed into the plane of the screen like this. So if I assign the direction to the electric and the magnetic field along with the velocity, so we can say that they are somewhat like this. So this is the value of electric field which is directed along the x-axis, the velocity vector is along the y-axis, and the magnetic field is in the negative z-axis direction. So as a result of which, if we calculate the force due to the electric field, so the force due to the electric field which will be equal to QE will be acting in the I cap direction, that is in the direction of electric field, and the magnetic force will be acting in the direction of QV cross B. So velocity is in the J cap direction cross magnetic field, where magnetic field is in minus B K cap direction. So if we perform the cross product, so the value of J cross K is going to be I. So we already have a negative sign, so we write it as minus QVB in the I cap direction. So over here, if I wish that the particle passes this region without any deviation, so I am writing in order to pass this region without any deviation, so I can say that the net force must be 0. So if net force is 0, then Fe and Fm, which is equal to F net, must be 0, and if it is equal to 0, so we can say from here that the value of electrostatic force must be equal to the magnetic force, and we can say that QVB is equal to QE. So the value of velocity V is equal to E by B. So this is the velocity which is needed for the particle to pass the region without any deviation, and hence this device is also regarded as velocity selector or velocity separator, as this helps us in identifying the slow moving as well as the fast moving particles. So the next concept that is associated with this force is a cyclotron. So we are going to study about cyclotron. So before initiating, we begin it in this way, that how a cyclotron is exactly looking like and what is the purpose of a cyclotron. So the cyclotron is a machine that helps us to accelerate the charged particles or the ions to high energies. So this is what this particular cyclotron does. So over here I am making a 2D arrangement. So 2Ds are basically the English alphabet Ds. So it is named as 2Ds arrangement. So the diagram looks like this. So the two Ds, which are two big Ds, look like this. and the region inside this D's is having a certain value of magnetic field. So it is having a value of magnetic field. So in this case we are taking the magnetic field which is directed into the plane of the paper, and the region in between the two D's is having an alternating electric field. So I will explain why I am saying alternating electric field and what purpose it is going to serve. So when I say that the electric field is alternating, so I mean to say that the direction of electric field will be in this direction for a certain span of time, and then it will alter itself, and now the electric field direction will be in this direction. So basically the electric field is going to change its sign alternatively in tune with the circular motion of the charge particle. When I say in tune with the circular motion of the charge particle, I mean something like this. Now watch very carefully because I will complete the diagram as I say. So suppose when the charge particle is placed over here, and if the electric field is towards the right, so if the electric field is towards the right, I will say P, and when it is towards the left, I will say Q. So as the electric field is towards P, so due to the electric field applied, this particular charge will start moving towards the right, and as it moves it acquires a certain velocity as it enters this D arrangement. Now because of the presence of magnetic field, it will deviate like this in a semicircular path and will again come in the region of electric field. Now the direction of electric field is in the direction of Q, and as a result of which again this charge particle will accelerate and will attain a certain speed and will again enter a region of magnetic field on the other side, this time with an increased speed. Again it will come in the region of electric field where electric field is in the direction of P, and again it will be accelerated because of the electric field, and then it again enters the region of magnetic field. This time it will cover a larger radius because the velocity is again increased because of the acceleration which is provided by the electric field. So again it will enter a region of electric field which is switched in the direction of Q, which will again accelerate, and this process will continue till this charge attains a very high velocity, and eventually this charge will move out of the cyclotron. So there will be an exit port. So the port is decided as per the need. So it will come out with a certain value of velocity. So for the equation of velocity, I can say when it is moving in a circle of radius capital R and magnetic field is B, mass is m and charge is q. So the value of velocity can be written as qbr by m. So it is equal to qbr by m, where r is the radius of the trajectory at exit. So r is the radius of the trajectory at exit, and hence I can say that the kinetic energy attained by ions can be written as Ke, which is equal to half mv square, and if we square the equation we obtain q square b square r square upon 2m. So this is the value of kinetic energy of the charged particle which is accelerated using the cyclotron arrangement. So these are the two devices which we use which is based on the working of combined electric and magnetic field.